In this video, we're going to look at an interesting case that can arise when we're using the law of sines. We call this the ambiguous case, and what it really means is that it's possible to have a set of given information for a triangle that includes what we would normally use for the law of sines, which is having an angle measure that we know and a side length opposite that angle that we also know the length of. And yet, the information doesn't actually uniquely produce one triangle. We get two possible triangles that can be formed, and therefore when you're given a certain set of information, sometimes you need to provide information for two possible triangles. So, for example, if we're given the information that we have a triangle ABC, and the measure of angle A is 45 degrees, AB is 17 centimeters, and BC is 14 centimeters, when we go to try to draw that triangle, you're going to see that there's two possible triangles we could create. So we start off by drawing a 45-degree angle to represent that angle A. And we're going to place a point B somewhere along that one of the rays here, such that we get a length of 17 centimeters. Right, so that's drawn here in the next stage. So we have the 45-degree angle, we have the 17 centimeter side length for AB. The next step is to use the final piece of information that BC is 14 centimeters. So going from B here, we're going to draw down to this second ray, we're going to draw a side length that's 14 centimeters. But there's actually two ways we can do this. Because the angle here at vertex B is not fixed, we don't actually know what its measure is. Any angle measure at vertex B could be viable as long as it places point C on this ray of angle A, and that it makes BC 14 centimeters. And you can see there's two actual places for that. Right? C could be located here, or C could be located here. We still get 14 centimeter side lengths for either of those cases. So this creates the two possible triangles shown here. So we have a 45-degree angle followed by a 17 centimeter side length, followed by a 14 centimeter side length, and that's true for both of these triangles. The main difference you'll see is that in one of these cases, angle C is an acute angle, and in one of these cases, angle C is an obtuse angle. Obtuse angles are larger than 90 degrees. Now in the lesson, it goes through the example of finding all the missing information for these two particular triangles. So I'm going to show you an example using a different set of measurements and go through that. So suppose that we're given, again, a triangle ABC, where AB is given as 24 inches long, BC is 9 inches, and the measure of angle A is 18 degrees. So when we draw that 18-degree angle down here at vertex A, then we place B along one of the rays of A so that we get a 24-inch side length. We do that in both triangles. And this third side, because it's shorter than AB, could land at two different spots. It could either be here at 9 inches, or it could land here at 9 inches. And that second case is what we've drawn down here as the second triangle. So again, we get two possible triangles, and the key difference of them being that in one case, angle C is an acute angle, and in one case, angle C is an obtuse angle. So let's figure out the missing information. So let's start with the case where angle C is an acute angle. So angle A and its opposite side length are the pair that we know, and we're going to look for the measure of angle C. So the measure of angle C, the sine of that, divided by the side length C has got to be the same as the ratio of the sine of the measure of angle A divided by the side length of A. So in other words, the sine of the measure of angle C divided by 24 inches has got to be the same as the sine of 18 degrees divided by 9 inches. So then the sine of the measure of angle C is going to be 24 times the value of that ratio. And for purposes of this video, I'm just going to go ahead and calculate this off screen. You can verify this with a calculator. That 24 times the value of that ratio is approximately 0.824. So then the measure of angle C is the arc sine, or the inverse sine, of that value. which is about 55.49 degrees. So I encourage you to grab a calculator and check my work there. So we'll come up here to our diagram and we'll add 55.49 degrees for angle C. That leaves two more pieces of unknown information for this triangle, the angle measure B, as well as the side length AC, right, which would be the side length B. So the sum of these three angle measures has to be 180. So again, if you grab a calculator, you can check my work. But that's going to mean that angle B is going to have to be 106.51 degrees. And the last thing to figure out is the side length for B. So here we're going to have B over the sine of the measure of angle B. And again, I'm going to use the angle and side length pair for A here. And I'll fill in the information I know. So we multiply by the sine of 106.51 degrees. Again, I'm going to calculate this off screen. I encourage you to grab a calculator and check my work. It's going to give us that B is approximately 27.92. So we come up here, 27.92 inches. Again, a quick check is usually a good idea here. The largest side length is going to be across from the largest angle measure, and the smallest side length will be across from the smallest angle measure. So 18 degrees is the smallest angle measure, 9 inches is the shortest side length, so that makes sense. 106.51 degrees is the largest angle measure, and 27.92 inches is the longest side length. So it seemed to check out. So that was for the first possible triangle. There is this second possible triangle that does meet the given information about triangle ABC. And so what we're going to do is we're going to figure out the measure of angle C if we assume that C is an obtuse angle. Now when we begin this process, we want to find the sine, the measure of angle C, divided by the side length C, and we'll compare that to the sine of the measure of angle A divided by the side length A. So then sine of the measure of angle C divided by 24 will be equal to the sine of 18 degrees divided by 9 inches. So the sine of the measure of angle C will be equal to 24 times this ratio. Before I do any calculations, come back up here and see that we actually get the exact same statement that we got in the first case. So when we finish this off, we're going to find the same result. It's going to tell us that angle C is approximately 55.49 degrees. But that can't be, because angle C is an obtuse angle. And this is clearly the measure of an acute angle. So we have a problem. This is the big thing we've got to be able to figure out and recognize when we're working with this ambiguous case, is how do we get an angle measure that satisfies the law of sines and yet is not an acute angle measure. So this is where we've got to go back on our understanding of sine functions and what they represent and how different angle measures could produce the same sine value. So let's really quickly just go back here and sort of sketch the unit circle. The sine values, if you remember, are the y values, those vertical leg lengths, or those vertical distances above the horizontal axis, given the angle measure. So if we draw a 55.49 degree angle on the unit circle, whatever its y value is here, this is the value of the sine of that angle measure. But any angle measure that produces the same y value is also going to have the same sine value. So in other words, we're also going to get this angle measure here that's going to produce the same sine value. So we use symmetry. So So this angle here is also going to be 55.49 degrees. So what we need is an angle measure that is 55.49 degrees short of 180 degrees. So in other words, the angle measure we're looking for is not 55.49 degrees. We're looking for 180 degrees minus 55.49 degrees. So the supplementary angle to 55.49 degrees. And that's 124.51 degrees. And feel free to check my work on that. So let's add that to our diagram. So the measure of angle C is 124.51 degrees. We know that the three angle measures inside the triangle have to add up to 180 degrees. So that'll allow you to figure out the third angle measure in the triangle. So I'll leave that to you to do on your own. The final piece of information is going to be the length of side AC here, right, which is the length B in inches. So you'd set that up by doing B over the sine of the measure of angle B and set it equal to another one of the ratios, so like side length A divided by the sine of the measure of angle A. So once you figure out what the measure of angle B is, put it in there for the measure of angle B. Go ahead and insert the information you know for the ratio over here, and you can finish solving off for B. And I'll leave that to you. But this is the method for finding the information for the two possible triangles produced when you get this ambiguous case. And again, these ambiguous cases arise typically when you have information where you know an angle measure and two consecutive sides in a triangle, where this side that's opposite the known angle measure is actually shorter than the side adjacent to that angle, which is going to allow you to have, basically two different places where that side could end up on that other ray.